Hello, welcome to the online version of Physics 103. Today we are going to talk about force and Newton's laws of motion. So we are going to talk about force, meaning our in our discussion we are going to include force. Okay, it means now we are going from kinematics to dynamics. Okay, all right. So first of all, let's talk about the concept of force, mass, and weight. Okay, so what is a force? The simple definition of force is a push or a pull, right? Okay, and what is mass then? Mass is amount of stuff. Suppose you have some object, and what is the amount of stuff, or what is the amount of matter contained in it? So that's the mass. So what is weight? Weight is pull on the stuff. Pull on the stuff, meaning mass, right? So pull meaning it's the force, right? So what kind of force is it? It's the force due to gravity. Okay, force due to gravity, right? So what is the force due to gravity? Mg, right? Okay, mass times acceleration due to gravity. So on the surface of the earth, what is the value of g? G is 9.8 meter per second squared. But by the way, g is planet dependent. Planet dependent. So if you go to different planet or moon, for instance, then the value of g decreases. Okay, so what is the value of g in this case? In moon, g moon is almost 1/6 of the value of g on the surface of the earth. Okay, g is small. So what I'm trying to say here is g is planet dependent. Okay, next thing we'll be doing here is uh, Newton's laws of motion, right? So there are three Newton's laws of motion. One is first law, the other one is second law, and the third one is third law. Okay, names are very easy. First law, second law, and third law of motion. So in this case, we begin with Newton's first law of motion. What does the first law tell us? An object continues in a state of rest or in a state of motion at a constant speed along a straight line unless compelled to change that state by a net force. Okay, that's the Newton's first law of motion. So meaning in this case there are two sections here, two parts rather. So one is state of rest, right? One is the rest, the other one is motion. Okay, so this is the example where the object is in the state of rest. So in this case, the object is in the state of rest. Why? Because net force is 0. Okay, net force, remember net force is 0. So there is gravity here. Gravity is pulling this down, which is mg, right? So there is force then. But remember, I call net force, not force. Okay, net force is 0. How do I know there is no force? There is no net force because this guy is not moving, right? But we can see the force here. Then if there is force, how come this guy is not moving, right? That's the thing. This guy is not moving even though you have mg there, because the surface here, okay, has normal force here, right? There is a normal force perpendicular to the surface. So this normal force happens to be equal to this mg. Normal force is positive direction, mg is a negative direction. If this is half kg, this is minus half kg. So what is the plus half minus half? Is 0. So meaning net force is 0. Since net force is 0, this guy does not move. That's what Newton's first law of motion tells us. If the net force is 0, the object which is at rest remains at rest. That's what is happening here. In the same way, an object which is moving, right, which is in the state of motion here, which is in the state of motion, okay, keep moving with constant speed along a straight line. It does not change the direction, just keep moving in a same direction, unless compelled to change that state by a net force. Let's take a look at this example here, this GIF, okay? So if you consider from here to here, right, what is happening, this part of the motion, this guy is moving from here to here, keep moving in the state of rest, sorry, in the state of motion, right? So this guy keeps moving in a straight line with constant speed, okay, until here, until this position, okay, according to Newton's first law. An object continues in the state of motion at a constant speed along the straight line, meaning from here to here, okay? But what happens right at this point? Right at this point, there is an obstruction to the path, right? So meaning this creates the opposing force here, okay? The net force is no longer zero now. So this guy was moving in this part of the motion, but right here there is an obstruction, meaning net force. Due to the net force, this guy changes the state of its state, meaning it goes from motion to rest, okay? So it is the force, this force, that causes the change of state from motion to rest, okay? So again, what is the conclusion? If the object is at rest, this guy continues in the state of rest if net force is zero. And if the object is moving, then it keeps moving with constant speed along the same direction as shown in this box here, okay? Because in this box there is no net force, okay? So when there is net force, then it changes the state, meaning from motion to rest. Okay, let me write whatever I mentioned here. So if there is no force, no change in state. No force, no change in state. And if there is force, then there is change in state, inverse, change in state. Then can you conclude something about the force here from this to a conclusion? So what is force then? Can I say the force is something that causes the change in state? Force is something that causes the change of state, meaning if the object is at rest, it goes to motion. If the object is in motion, it goes to rest, okay? That's called change of state, right? So in that sense, Newton's first law of motion gives the qualitative definition of force, okay? So it does not give me how much force is there, but it gives me there is force because there is change of state. When there is change of state, it means there is force. How much? We don't know. That's why we say the Newton's first law of motion gives you the qualitative definition of force, not the quantitative. You don't know how much, but you know it is there, okay? That's the qualitative definition. All right, so what is net force then? Net force is the vector sum of all the forces acting on any object, okay? Suppose you have an object here, okay? You have two forces acted on this object. One is 10 Newton to the east, so you can call the east the positive direction, and the other force is 4 Newton to the west, right? Let's say negative, right? Then what is the net force? Meaning plus 10 minus 4. How much is the net? 6 Newton plus. Plus means east, right? That's the net force. Okay. So this is the definition of net force. Mathematically, force is net force is written as sigma F, meaning that suppose there are F1, F2, F3, dot, 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 dot. There are many forces acting on an object. Then what is the net force? Add them all together, taking the sign into account. Remember, in the previous case, one is plus, the other one is minus. Okay. So what is plus, what is minus? Plus 10 minus 4, right? So take the sign into account and add them together. So when you add them together in that way, that force is called net force. Okay. And when you add, we can simply write summation F, where this summation, we call it summation, but that letter is Greek letter sigma. Okay. What does that denote? That denotes the vector sum. By the way, what is the unit of force? As you know, unit of force is Newton. Okay, we can write N, right? All right. Okay, in this slide, I'm going to talk about inertia. Okay, inertia is the natural tendency of an object to remain at rest or in motion at constant speed along a straight line, meaning without changing the direction. Okay, let's say what I'm meant by that. Suppose you have an object here, which is 100 kg, right? So this guy, if you push this guy versus there is another object here, which is, let's say, 50 kg. So which one is easier? Both of them are at rest. This is at rest. This is at rest. Which is easier to push? So definitely this guy is, let's say this is A, this is B. B is easier to push. You know why? Because B has less inertia. This has more inertia. Meaning it has more tendency to stay in rest, at rest. Okay. So inertia is some sort of property or tendency of an object which wants to remain at rest if it is at rest. Okay. So in this case, both of them wants to remain at rest because they are at rest. But which has more tendency to remain at rest? Obviously, this guy has more tendency to remain at rest. Okay. Similarly, if you have two objects here, the same object, right? Let's say, then this guy is moving. This is 100 kg and this is 50 kg again. Both of them are moving. If you want to stop here, you want to stop it here, stop. Right here, you want to stop it here, stop, stop. If you want to stop, then which one is easier to stop? Definitely this guy is easier to stop because it has less inertia. Less inertia. This has more inertia. Meaning an object which is in motion has the tendency to keep moving at constant speed without changing the direction. Okay, so that tendency depends on the mass. Okay, bigger the mass, greater the tendency. Meaning, since this guy has bigger mass, it has greater tendency to keep moving. That's why it is difficult to stop here. And this guy has smaller mass and has less tendency to keep moving. So that's why this is easier to stop. Okay, so that's the inertia. So as it is clear from here, a mass is the quantitative measure of inertia. Okay, so bigger the mass, more the inertia, right? So we can conclude that bigger the mass, Okay, bigger the inertia. So from the previous example I showed, it is very clear, right? Bigger the mass, bigger the inertia. Okay, all right. So now if you take a look at this inertia here, so does this look like similar to the first law of motion? It's kind of, right? It's kind of first law of motion. This is what we did in first law of motion also, right? So what is the difference though? Because inertia is the property or tendency of an object to remain at rest or keep moving at constant speed along the straight line. Okay, but what is the first law of motion? First law of motion is the process. Okay, process. So this is inertia, property is the inertia, process is the first law of motion. Meaning, because of this property or inertia, we see the process, which is first law of motion. Okay, so they look similar, but they are not, right? So one is property, the other one is process. All right. So by the way, first law of motion is also called law of inertia. Law of inertia. So you know why, right? Because they are very similar, you can see. So this is also called, the first law is also called law of inertia. All right. First law of motion, we said that it gives you the qualitative definition of force, right? Qualitative definition of force. So what does Newton's second law do is it gives the quantitative definition of force, meaning you have a formula. Okay, so you know how much force is applied. Okay, that's how you that's what Newton's second law does. Okay, it gives you quantitative definition of force. So meaning the net force equals ma. Okay, net force equals mass times acceleration. Okay, then from this equation, what is your a? Divide both sides by m. What do you get? You get net force over m. Net force over m gives you a. So acceleration is net force divided by m. So you know the force is vector, right? And so is acceleration, right? So what is the direction of acceleration? If the force is upward, then acceleration is upward, meaning the direction of acceleration is same as the direction of the net force. Okay. All right, before we move on to third law, let me talk about forces, equilibrium, and free body diagrams. This is very important. So what is force? We already know that. Now I briefly introduce equilibrium here and free body diagram. Okay, free body diagram are very important concepts. So as you can easily guess, is free body diagram, right? So free body diagrams are one of the most important things for you to know. How to draw and use in problem solving. Okay, in solving problem. Okay, so we'll talk more about that in the next slide with an example. So this is very important for drawing and using in solving. It is very important to draw a free body diagram because it can be used in solving problems. That's what I meant. All right. So why is it called free body diagram, right? Free, because suppose you have an object here. It is connected to something here. Let's say this is connected by rope, and this object is on the surface like this, connected by the rope. You cut the rope and make it free. So a diagram of a body isolated from its environment. That's what I meant. Okay, you isolate, but remember, while you isolate, you have to consider the external force acting on it. Even though you cut the rope, you cannot ignore the force due to the rope. Okay, this is the force due to the rope, which is tension force, right? Tension is also a force. All right. So why is free body diagram so important? Because it simplifies the problem a lot. Okay, because you can cut it anywhere you want to, and you can analyze the problem. Okay, so it is key to being able to write equations of equilibrium, which are used to solve for unknown force and angles. Okay, what is equilibrium again? You say equation of equilibrium, right? Look at that, equation of equilibrium, meaning when the object is in equilibrium, what are the equations that describe that configuration, right? Equilibrium configuration. So those equations are called equations of equilibrium. By the way, what is equilibrium? Equilibrium, I'm going to talk about that later, but when net force is 0, we call it equilibrium. For now, I'll just, all right. Now, how does the free body diagram simplify your problem, right? So let's say you have an object here. It is hanging from point A, but there are other 2 ropes at B and at D. Okay, so this A is under the influence of 3 forces, one here, and one here. Okay, now in the free body diagram, what you do is you cut this. Suppose you want to find the free body diagram at point A, then you cut all those things here, cut here, and cut here. Then what I'm left with, once you cut, what do you show? You cut it, but don't forget the force. Okay, there, meaning you have to show all the forces. So you cut it. See, we cut it here, cut it here, cut it here. Okay, there's nothing there. So we might have realized here, right? See, we cut here, but we consider the force acting on A. So what is the force acting on A? One is towards D, this is the force. One is towards B, this is the force. And one is towards, it's downward, right? This is the force. This kind of diagram is called free body diagram. Meaning, again, if we have a system like this, cut it free and just show all the forces acting on that particle. Okay, that's called free body diagram. Okay, then once you do that, what do? You show all the forces there, right? So now what is the force here? This is the direction of force. What is the magnitude of force? Do you know the magnitude of this force? So this magnitude you can call, I don't know, FB. Okay, you can call FC. The magnitude of this force is FD. You know, you can call, like, you can denote like this too, you know, which means it contains both magnitude and also direction. Okay, so this is called vector, right? If you have the arrow on the top, it means vector, meaning it represents both magnitude and direction, right? All right, so now, by the way, there are 2 forces there, 2 kinds of force. One is active force and the other one is reactant force or contact force. Okay, active force, they want to move the particle. And what does the reactive force do? They tend to resist the motion. Okay, that's the difference between active force and reactive force. When I say show all the forces, what kind of force you are supposed to show? You show both active and reactive force. Okay, so all the forces. So now this is FD, as we said earlier, this is FB and this is FC. So what is FC? FC, we know FC, right? This is acting down. So what is the object hanging here? 40 kg. But how do you convert mass to force? Weight, right? In this case, force is weight, mass times gravity. So 40 times 9.8, 40 times 9.8, that happens to be 392.4 Newton. Okay, so now you have the free body diagram. Okay, so it is very important, you will realize. Now you know how to draw it. Now in in the coming slides, I'll teach you how to use it. Okay, this is very good, important concept. All right, let me give you one more example of free body diagram right here. So now you have a car here, and the car is being pushed by two people here, and one person applied 395 Newton and other person applied 275 Newton force, and there is also opposing force of 560 Newton. So what are the force on the right side? This way. So 275 plus 395. Okay, these are the force on the right. And what is the force on the left? You have this force on the left. Okay, is there any force on the up and down? There might be, but the net effect is zero, right? Because the downward force is weight, right? Upward force is normal force. So that's why the net effect in the perpendicular direction or vertical direction is zero. That's why we didn't show them here. That's why it's not there. Okay, you just have the force on the left and right. So what is the total net force in this case? Now this is free body diagram. Look at that. This is free body diagram, and this is just a point, right? Which is the representation of the car, right? So this is how physicists represent an object. Any object just represented by a point. That's cool. All right. What is the net force then? Net force. So plus 275 plus 395 minus 560, right? If you do that, how much do you get? You get 110 Newton. And of course, this is plus, right? Then what does this plus sign signify? Plus sign tells me that it is directed to the plus x-axis of the coordinate system. Okay, that's the total force or net force, right? Now, if you know the net force, and you can find the acceleration, right? Given that you know the mass of the car. So suppose I give you the mass of the car, which is 1850 kilogram. Then how do you find the acceleration of the car? Net force, right? Net force divided by m. This is Newton's second law, remember? So then what is net force? Net force is 110 divided by mass is 1850. So what is that? If you do that, I will give you the number here, 0.59. So what is the unit? Net force, what is the unit? Newton. What is the unit of mass? Kilogram. So the unit is Newton per kilogram. Also, this can be written as meter per second square, which is your familiar unit of acceleration, right? Which is 0.059. So acceleration has two units, Newton per kilogram and meter per second square. By the way, they're exactly same, because if you convert this Newton to fundamental units, right, then you happen to get this. Okay, so you can write either Newton per kilogram or meter per second square, but we are so used to meter per second square in kinematics that we don't do that. We don't do Newton per kilogram. We just simply write this. Okay, this is the unit of acceleration with the magnitude equals 0.059, right? Okay. Okay. In this case, we'll be talking about when is net force zero, and when the net force is zero, what is that condition called? Okay. So this is what we are going to talk about in this slide. So when I say force, summation F equals ma, right? So this guy is zero. Okay, that's what we are seeking. When the net force is zero, it means this is zero. Okay, so let me write this in more expanded form here. So A is what? So A is this from previous chapter. A equals B minus B0 over T, right? So you can write this guy here, B minus B0 over T. Then, so the net force is equal to, then what is your conclusion? Net force equals to M B minus B0 over T. Now this guy must be zero. When net force is zero, it means this guy is zero. Makes sense? So when is this guy zero? So This guy is 0 when the top is 0, right? So when I say top equals to 0, you have mb minus b0 equals 0. It means m cannot be 0 because m is always non-zero. Okay, it's the quantity of matter, right? The quantity can never be 0. Suppose you have an object here, wherever you take it, the quantity of matter in it is not 0, right? So this m can never be 0. The only thing that could be 0 is this guy. If you multiply this and this together, you get 0, right? So since mass cannot be 0, but the product is 0. If you multiply these two, you get 0, but mass cannot be 0. It means there should be something 0, right? Otherwise, you cannot get 0. Okay, so these should be 0. Then m times 0 is 0. That makes sense. So meaning b minus b0 should be 0. Otherwise, this product cannot be 0. Okay, so b minus b0 equals 0, meaning what? B equals b0. So this can be achieved under two circumstances. One at rest, the other in motion. Okay, when at rest, b equals to b0, meaning what? Rest meaning 0, right? Velocity is 0. Meaning if something is at rest, means velocity is 0. Meaning initial velocity is 0, final velocity is 0. That's the rest position, right? So when that happens, the net force is 0. Okay, that's the condition number 1. Other thing is that even in motion, b can be equal to b0. What is that condition called? That condition is called constant velocity, meaning initial velocity is, let's say, 5, the final velocity is 5, meaning you have constant velocity. Then you get b equals b0, right? Okay, so in that case, when b equals b0, 5 minus 5, suppose this is 5, this is 5, 5 minus 5, 0. Did you see that? It means the net force is 0 when the velocity is constant. Okay, so there are two conditions when the net force is 0. 1, when the object is at rest. 2, when the object is moving with constant velocity. Make sense? So those are the two conditions. So when b equals b0 equals 0, that condition is called static equilibrium. Static equilibrium. When b equals b0, but they are not 0, that's the dynamic equilibrium. Okay, there are two kinds of equilibrium. One is static equilibrium, the other one is dynamic equilibrium. Okay, so let me summarize. When the object is at rest, that's called static equilibrium. When the object is moving with constant velocity, in that case, the equilibrium is called dynamic equilibrium. Okay, all right, let's talk about Newton's third law of motion here. So whenever one body exerts a force on second body, the second body exerts an oppositely directed force of equal magnitude on the first body. So you can see here the guy is tossing the ball. Okay, so the force due to man to the ball is equal to the force due to ball to the man plus cart. That's the meaning of Newton's third law of motion. Okay, the force exerted by this man on the ball, this ball, is equal to the force exerted by the ball on the man. Okay, remember that there should be two bodies there. One is ball, B-A-L. One is ball, the other one is man plus cart. Man plus cart. There are two systems there. Man plus cart is one system, ball is another system. So ball impose the force on this, and man plus cart impose the force on this. Okay, so both those forces are equal and opposite. That's called that's the Newton's third law of motion. Okay, now if you use the Newton's second law of motion, what is the force of man to the ball? M ball times A ball, right? Okay, then similarly, what is the force of ball to the man plus cart? M mass man plus cart plus acceleration man plus cart. For instance, in this case, let's say mass of the ball is 0.5 kilogram. So acceleration of the ball is 50 meter per second square, and mass of the man plus cart is 100 kilogram. What is the acceleration of man plus cart? Can you figure this out? So according to Newton's third law, so what happens? So this multiplied with this equal to this multiplied with this, but opposite sign here. So meaning, let me write mass of the ball 0.5 times acceleration of the ball 50 equals minus 100 times A. That's what I meant. Okay. So from here, how do you find the acceleration? Let me do it here. Okay, up here. So divide both sides by 100. What do you get? So this 100 cancel out. You get what? 50 times 2. Okay, so 0.25 meter per second square. Acceleration of the man plus cart is negative 0.25 meter square. Negative meaning it's the opposite direction. So what is the acceleration of the ball? 50. Okay, acceleration of the ball is 50 meter per second square. Acceleration of the man plus cart is negative 0.25 meter per second square. That's why this guy moves very slowly to the backward direction, but the ball seems to be moving faster, right? Okay, this is Newton's third law of motion. All right, now in this case we'll be talking about tension and normal force. Okay, tension and normal force. So tension is the force exerted by a rope, string, chain, or cable. Suppose you have an object here. It is hanging right from the rope. Maybe, I don't know. It could be string, chain, cable. Okay. Then this guy is pulled downward by mg force, but this guy is not moving down. Why is that? Because net force is 0. How come? Because there is a force acting up, okay, which is called T. This is, let's say, I don't know, plus 10 Newton. This is, let's say, minus 10 Newton. Downward is negative, upward is positive. How do I know they are exactly same value? If this mg is negative 10, then this tension should be 10 Newton also. Why? Because this is not moving. There should be equal and opposite. Okay, this tension is a force. Okay, tension is a force. Then there is another kind of force which is normal force. Okay, so suppose this is an object here. It is resting on the top of the on this table, right? And there is a force acting down, obviously, which is gravity. But why is this guy not falling down? Because the surface is exerting normal force, okay, perpendicular to the surface in contact. That's why this guy is not moving down. It means there is downward force equal to normal force in opposite direction. They balance each other. That's why the net force is 0. When net force is 0, there is no change of state, right? So that's what it is. Now, in this case, let's talk about this is an example, okay? So there is a 5 kilogram mass hanging from a rope. This 5 kilogram, okay? So mass is 5 kilogram. Hanging from a rope, what is the tension in the rope if the acceleration of the mass is 0? So what is your net force here? Net force is, one is T, the other is mg, right? There are two forces. One is T up, mg is down. So take the proper sign into account. So mg, you want to consider downward negative and upward positive. So meaning mg is negative, T is positive. That's the net force. So since the acceleration of the mass is 0, what is the net force? M times A, 0. Does it make sense? So then what is the tension? From here, what is the tension? Tension equals mg. So what is your mg? M is 5, G is 9.8, obviously. Then it is like 49 Newton. Does it make sense? Now, now assume an acceleration of 5 meter per second square upward. Now, the mass is moving up. Unlike in part 1, which is in that case acceleration was 0. Now acceleration is not 0, acceleration is upward. So 5 meter per second square upward. Okay, so meaning net force is T minus mg, obviously, right? That's the net force. Then what is the acceleration? Acceleration is this should be equal to, sorry, this should be equal to ma, right? So what is m? M is mass does not change, right? It's the same thing. So A is 5 meter per second, so upward, meaning upward means plus there times 5. Does it make sense? So then how do you do that? So T equals mg. Mg is 5 times 9.8, right? Plus 5 times 5, 25. There. If you do that, what do you get? 49 plus 25, right? So which is equal to 74 Newton. Now assume a downward acceleration of A equals 5 meter per second squared. Again, Newton's second law of motion, you have summation F equals ma. What is your net force? Summation F is net force, which is T minus mg, as you know, and equals ma, right? So T equals mg plus ma. What is your m? Actually, m is common, right? You can factor out g plus a. So m is 5. What is your g? 9.8, obviously. What is your a? A is downward acceleration, -5 there. Okay, so this, if you do that, what do you get? 5, you get 24. Okay, that's what it is. All right. So in this slide, I'm going to talk about apparent weight. Okay, so first of all, what is true weight? True weight is mg, right? Mass times acceleration due to gravity. Due to gravity. Okay, that's the true weight. So what is the apparent weight? Apparent weight is the weight of an object shown by the weighing machine. Okay, so that's the apparent weight. So apparent weight is equal to the normal force that the man or anybody which is on the weighing machine exerts on the scale. Okay, it's the normal force, meaning your weighing machine, suppose this weighing machine is at rest and this is on the flat surface, right? This is the weighing machine and you are on the weighing machine, right? So what does this weighing machine read? This weighing machine reads your reads the normal force. Okay, normal force. So what is normal force? Normal force is equal to mg in this case, because this is on the flat surface and the weighing machine is not moving. In that case, your mg is equal to the normal force. So even though weighing machine measures normal force, it means it is essentially measuring your weight, which is mg. So in this case, your apparent weight is equal to true weight, but they are in opposite direction, remember. But it doesn't matter, right? Okay, because your weight is weight. Okay, so normal force is equal to the weight. Okay, that's why your apparent weight happens to be equal to true weight. But what happens if the person is moving up? Let's say this is an elevator. Elevator is moving up. Okay, so as you can see here, you have 1,000. Okay, so you have 1,000. This machine shows 1,000 here. So, but the elevator, when the elevator is at rest, which is which measures the, in this case, the weighing machine gives you the exact weight. In this case, apparent weight is equal to true weight. That's why the exact weight is 700 here, but this elevator moves up. In that case, what happened was your weight is bigger than the true, the real weight. But if the elevator is moving down, what happens is your weight is less than your real weight or true weight. Okay, how is this possible? How is this possible? Let me show you here. So in this case, net force weight is down, the normal force is up. So N minus mg is the net force. Okay, that must be equals to ma, right? Okay, so it means in this case, what is your A? 0. It means A is 0, meaning from here N minus mg equals 0. It means N equals mg. Look at that. Okay, this gives you this. Okay, so that's why your weighing machine gives you the exact weight. But how about here? In this case, your A is non-zero because this is moving now, meaning moving up. So moving up means A is positive. Okay, so what happens in this case is N becomes mg plus ma. Isn't that right? How? Let me show you here. Add mg on both sides here. Then this and this cancel out. Then what do you get? N on the left hand side and this guy on the right hand side. By the way, you can factor out m from here. M a plus z. Look at that. So your weighing machine, which gives you the normal force, right, is now bigger because you have to add g to the a and multiply to m. That's why it's bigger here. But how about if it is going down? If it is going down, what happens? Let me show you here. If it is going down, this guy is negative. Net force is this is the net force. But when it is goes down, your ma is negative. That's why what you got here is if you add plus ma on both sides, sorry, plus mg on both sides, what do you get? This mg cancel out. You have n equals this. N equals, n is on the left, right? This is n. And what is this guy? G minus a. I put the positive first, then negative, okay? You can factor out m, then g minus a. So what is your g? G is 9.8. Then whatever acceleration, you have to subtract. That's why it less. It is less, okay? Now, there is another extreme case here. Let me show you. This is very interesting. There is an extreme case here. What happened here is when the net force is equal to mg. What do I mean by that? Meaning something happened here. Crash. Okay? See that? Meaning what happens is this elevator falls freely. Okay? When it is falls freely, it means what is the acceleration? What is the downward acceleration? Free fall, meaning a equals g. Okay, so we know this is, it is going down, meaning minus ma, but your a happens to be g. Look at that. Okay, so then what do you get? N, sorry, if we add mg on both sides, what do you get? Mg 0 and this is 0. What do you get? N equals 0, meaning n is the weight given by the weighing machine, right? Meaning your weighing machine gives you exact 0 here, meaning that's called weightlessness. What is that called? Weightlessness. So the two way you can get weightlessness is either you go to the space, there is no weight, right? Or you happen to be in this kind of unfortunate situation, okay, then you will have zero weight. All right. All right. So let me show you this interesting situation here. So when a equals 0, this guy is at rest, you have normal weight. When this guy is moving up, you have the greater weight than the normal weight. When this guy is moving down, you have less than the normal weight. When a equals z, then you have zero weight. Okay, this is what I'm going to show you here. All right. Now, all right, so let's do a problem here. So here, 75 kilogram man stands on a scale in an elevator. So this is a man standing on the scale. Okay, when the elevator begins to rise here, the scale reaches 100 kilogram. Okay, what was the acceleration in factors of g? All right, let's do that. So what is the normal force? Normal force is acting up. What is the downward force? Downward force is mg. So upward is positive, downward is negative, right? So what is the net force? N minus mg. That's the net force. According to Newton's second law, what is your net force? Net force is ma, right? Our net force is this guy here. So that must be equal to ma. All right, m times a, right? So what is n? N is 100 times acceleration due to gravity. How do I know? Because n is here, 100 kilogram. So how do I change my mass to force? Weight, right? How do you change your mass to weight, rather? So the multiply by acceleration due to gravity. 100 times g minus m is how much? Real weight, real mass is 75. G is g because m is 75, a is a. So now how do you find your a from here? Well, let's do this. If you divide this guy by 75, what do you get? 75, right? So then 100 minus 75, 25g over 75 equals a. This cancel out, so this is a. So this means a equals 1 over 3g. See, I did not put the value of g here. Why? Because we have to find the acceleration in factors of g. That's what it is. So acceleration is 1 over 3 in factors of g. Okay. Okay, so in this slide, I'm going to talk about spring force. So first of all, take a look at this experiment here. Okay, what happened here is if you have one weight, then you have certain extension. And if you have two weights, rather, you have longer, more extension, rather. So meaning the spring has more extension as we keep on increasing the weight, right? So weight is extension, I call it x is proportional to weight, okay? Or you can write this guy as this also, okay? So if you replace this proportionality by equal sign, then you have to write a constant here like this. This constant is called spring constant. And spring constant is property of spring, and it is constant. And K varies from spring to spring, okay? So for a particular spring, K is constant, right? So as you can see here in this GIF, so there is a weight, meaning there is a downward force, mg. Okay. So why is this guy not falling on the ground? Because even though there is weight acting downward, there is some force acting up, which is called spring force. They are equal and opposite. If this is plus, this is minus. Okay. They are equal and opposites. So meaning F is equal to minus W. Okay, so then this W is here, so minus kx. F is equal to minus kx. Okay, so this minus sign signifies that displacement and the force are opposing. Okay, they are opposite in direction. So by the way, this spring force, this is spring force is also called spring force is also called restoring force of the spring. Okay, restoring force of the spring. Okay, so what I meant by that is when you release this weight here, then what happens is the spring regains its original length. Okay, why is that? Because there is a force, which is spring force, that restores the original position. Okay, that's why this spring force, which is acting up here, this is also called restoring force of the spring. And this relation here, this relation, or you can say here, this, they're the same thing. And this relation is called Hooke's law. This is discovered by the scientist Hooke. Okay, you have Hooke, regular Hooke plus extra E. So this is Hooke's law after the name of the scientist Hooke. Okay, so as you can see here, you have a negative sign for the spring force, right? But in some practical purpose, you can write this guy simply as this, F equals Kx, meaning you just ignore the negative sign. Okay, even though you ignore the negative sign, you have to keep that in mind. What does this negative sign tell you? Negative sign would tell me that the force is restoring in nature, right? But for practical purpose, you can simply ignore the negative sign, but you have to keep in mind that negative sign is there. Okay, so that negative sign tells you the direction of the force, right? So simply find the magnitude and keep in mind that negative sign is there, meaning this F has the direction opposing to the force that extend the length of the spring. Okay, so let's do um, an experiment here, the virtual experiment. So if you keep on adding more and more weights here, the length of the spring becomes longer and longer. Okay, so the spring becomes longer and longer, meaning spring gets elongated, right? So suppose you have 1 kilogram of mass, 1 Newton, I would say. If you have 1 Newton mass, then you have the elongation by 3 unit. So keep on adding there the mass so that you will have more and more force. Okay, so then you have 4.5 unit of elongation, and keep doing it all the way to 9 unit of force. Then you have the elongation increases like this. For every weight you add on the pan here, the elongation goes on increasing like this. Suppose you have this kind of data. This is an example. And if you plot, this is weight, right? This is your elongation. We can call it X. So this weight, which is equal to F, the spring force in magnitude. So for now, I just care about the magnitude of the spring force because I know the direction is always opposite to the weight, right? So for now, let's not worry about the sign. All right, so if you have x-axis as elongation, this is your x-axis elongation, and y-axis is the force. Okay, this is your y-axis and this is force. Then if you plot this data, 1, 3, this is your 1, 3, okay, 2, 4.5, this is your 2, 4.5. So if you keep on plotting the data, then you will get this kind of data set, and you can fit the straight line. Okay, so if you fit the straight line, then you get the equation of a straight line to be y equals 1.5583 x plus 1.375. Okay, so this y is of course f, right? And this x is of course x, which is extension. Okay, and according to Hooke's law, what is the relation? F should be equal to k times x, right? We are ignoring the negative sign here, but keep in mind that it's there, and whenever you need it, you have to put it there. Okay, so now there is no c part here. There is no any constant, plus constant part is not here, but here you got the constant part. Okay, this is kind of error. Okay, this is the error. So don't worry about that error. Just Keep this in mind, and this is F, this is K, this is X. Okay, so this K is the slope, right? Because in the equation of a straight line, y equals, remember, y equals mx plus b. Okay, so this b is supposed to be 0, but that's okay. And here your x is x, this m is this guy. Okay, so this must be k, because if you compare these two guys ignoring b, then y equals mx compared with f equals kx, it gives that we get that k equals m, meaning the slope of this straight line here. Okay, so the slope of the straight line gives you the spring constant. Okay, this is how you find the spring constant. So if you in the lab, you will be given a spring, and so do the experiment, meaning keep on adding the weight on the pan and measure the extension and get the data like this, data set like this, and plot the straight line. And the slope of the straight line happens to be the spring constant. Okay, this is what you need to do in a lab. Okay, let's do a problem here. A coiled spring is stretched 0.05 meter by a weight of 0.5 Newton hung from one end. So now you need to find how far will the spring stretch if a 1 Newton force replaces the 0.5 Newton weight. Okay, first of all, you need to find the spring constant. Based on this data, can you find the spring constant? Okay, your force is 0.5 Newton, and your elongation due to this force is x equals 0.05 meter. So let's use the Hooke's law. If you use the Hooke's law, can you find the spring constant? Okay, so F is 0.5, then K is K, X is 0.05. You divide both sides by 0.05. You got, how much do you get? You got 0.05 here, right? 0.05. So K is 10. What is the unit? Unit is Newton per meter. How do I know? Let's see. What is the, let's take a look at this equation here. What is the unit of force? Newton. And what is the unit of K? We don't know. What is the unit of X? Meter, right? So then if you divide by meter on both sides, you got the unit of K. Okay, that's how you get Newton per meter. Okay, all right, so K is 10 Newton per meter. Now once you know K, now let's try to solve this problem. Part A, how far will the spring stretch if 1 Newton weight replaces 0.5 Newton weight, meaning this 0.5 is replaced by 1 Newton now. So use the same formula again, F equals Kx, right? Now we know the K, okay? So K is 10, and your force is 1 Newton now. So 1 times X. So what is your X then? X equals 1 over 10, which is 0.1 meter, right? And similarly, what weight will stretch the spring a distance of 0.03? So we know the K is the same spring. Once you determine K, you can use it again and again as long as you have the same spring. Then K is this, F equals Kx again, is the same formula, Hooke's law. Then F is unknown and K is 10. What is your X? Now your X is 0.03. Can you find your F? So F is 0.3 Newton. Okay, so thus you can figure out, you know, spring constant, you can figure out elongation, you can figure out force. Okay, so this is the problem in Hooke's law. All right, now let's do gravitational force. Okay, so you have two masses here, mass 1 and mass 2, and there is always a force of attraction between two masses. Okay, suppose to take any two masses, and there is always a force of attraction between them, and that force of attraction is called the gravitational force. Okay, and we can write the formula for gravitational force by using this formula. By using this is the formula for gravitational force, where F equals G m1 m2 over r squared, where m1 is the mass of this guy, m2 is mass of this guy, and r is the distance between these two masses. So we have r squared here, and you have a constant there. Okay, that constant is universal gravitational constant, and it is constant, right? So it has a value. The value of this guy is 6.673 10 to the negative 11 Newton meter square per kg squared. That's the unit. Okay. So as I said, two masses attract to each other, right? Let's say this guy is 1 kilogram mass and this guy is 1 kilogram. So this is 1 meter, right? So why don't they attract to each other and stick together if they have attraction, right? So let me put this number here. From this example, let me put the number in this formula. So G is 6.673 10 to the negative 11. Then 1 kg is, M1 is 1 kg. See that? Then M2 is also 1 kg. 1 times 1. R square is 1 square. So for simplicity, I chose 1 everywhere. So then what do you get? You got 6.673 10 to the negative 11 Newton, right? So which is very, very small force, because you have to divide. This means what? This means you have to divide 6.673 by this many zeros. Okay, 10 to the 11 zeros, meaning you have to have 11 zeros here. So which is very small number. That's why even though there is a force of attraction which is very small, that's why we don't see it, meaning practically that force is zero. But in theory, there is a force of attraction between them. Okay, so when the masses are big enough, like moon and earth, then you can definitely see the force of attraction, right? All right, let's do another problem here. So suppose this is M1 is like 12 kg now. Okay, so M2 is 25 kg, and the distance is, let's say, 1.2 meter, for instance. Okay, then what is the force of attraction between these two objects? Let's say 6.67 10 to the negative 11, right? Then 12, right? Mass, remember the formula, F equals M1 G M1 M2 over R square. G is this, M1 is 12, M2 is 25, and divide by 1.2 squared. Then if you do that, if you do the calculation, I have the number here, 1.4 10 to the negative 8, okay, Newton. So this is little bigger than the previous case, but still this is very small, because in the previous case we have 10 to the negative 11, now we have 10 to the negative 8. This is very small still. So that's why there is practically there is no force. In theory there is, but in practice there is no force there. Okay, let's do the free body diagram again. Okay, so let's revisit free body diagram. It's the same example from the previous slide. So you have this example here. What did we do in the last time? We found the free body diagram at point A. So what did you do? You just cut this free, right, and show the force. That's what we did, right? Cut this free and show the force. This force is FD, and this force is FB, and this force is FC, right? Okay, so you show all the forces. This is free body diagram. Now this is the free body diagram at point A. Let's do the free body diagram at point C. Okay, so how do you do the free body diagram at point C? Meaning this is the C point. Now cut this free. That's all. Okay, so now you have the free body diagram at C. So you cut it, but you have to show all the forces. What are the forces here? One force is acting down, which is gravity, mg. The other one is, what is the other force? Of course, this is tension force, right? Okay, so my C is like this. This is point C, and you have tension on the in upward direction and mg on the downward direction. So you have just two forces here. Okay, but you might wonder, okay, this C is connected to A, and which is A is also connected to B and D. Okay, will that further connection to B and D will affect my calculation? You might be worried about that, right? So You don't have to worry about that, because that's the beauty of free body diagram. You just cut it wherever you want, and you can analyze this chunk. Okay, if you want to analyze this this here, you just cut it here and analyze it. Okay, cut it here and analyze it, cut it here and analyze it, whatever you want. Okay, so nothing will affect that, as long as you have to you stick to the rule. Okay, cut it free and show all the forces, that's all. Okay, so it means free body diagram is an amazing tool that makes your life a lot easier. Okay, too much easy in problem solving. Okay, that's why I love it. All right, let's do one problem here. Here I have a mass m1 on the horizontal surface, maybe the table surface here. This is for now, let's say this is a smooth surface. Okay, we don't have friction, no friction. Okay, and this goes over the pulley here, and there is another mass m2. Okay, so hanging from the pulley, and this guy is moving down. Okay, so let's say the motion is downward. All right, so let's use free body diagram and find the acceleration of this downward motion. Okay, so for m2, let me start with m2. So let me make the free body diagram here for m2. Okay, this is my, you just cut it free, right? That's all, and show all the forces. That's all. This mg and the upward direction. What is the upward direction? In the upward direction, what is there? Tension, right? Tension is positive and mg is negative. So what is the net force? Net force is T and mg, but you have to show me the proper sign. So let's say upward direction is plus, downward direction is negative. That's why tension is positive, mg is negative. So this is the net force. According to Newton's second law, your net force should be equal to ma, right? So we have the net force. Then what is ma? M is m2. Then a is a. So downward is negative. That's why you have negative sign here. Makes sense? So from here, what is your tension? Tension equals mg. I should have written here m2, right? m2g. Okay. So m2g minus m2a. That's your tension. Now let's cut this guy free here. Let's cut it free here. Cut it free. So meaning you have m1. So you have tension here because this is connected to the by the rope, right? This is tension, and there is nothing, no force acting to the opposite direction because there is no friction. Remember, there is no friction. That's why your net force in this case is just tension. Okay, tension equals to ma, right? m1a. Okay, this m1, and acceleration is a because this direction is positive, this direction is negative. So when this guy moves down, this guy moves to the right. Okay, right is plus direction. Okay, so that's why T equals plus m1a. All right, now you have two equations here for the tension. T equals this and T equals this. So that these tension are same, right? So they are equal to each other. m1a equals m2g minus m2a. Okay, so can you find the acceleration now? m1a plus m2a equals m2g. Okay, so you can factor out a here. You got m1 plus m2 equals m2g, and what do you get? What is your a? A equals m2g over m1 plus m2. Okay, so if I give you, let's say your m1 is 1 kg, m2 is 2 kg. Okay, this is 2 kg, this is your 1 kg. Then what is the acceleration? Let's plug this in here. A equals m2 is 2 times m1 is 1, m2 is 2. Okay, and 1 plus 2, then g. What is the value of g? G is 9.8. Okay, so this is 2 over 3, 9.8. All right, and whatever you have, it is meter per second square there. Okay, all right, so why is our acceleration is positive here? It happens to be positive here, isn't it? which is not true because it is moving down, right? Acceleration should be negative, okay? But the thing we are getting here is positive. How come? Because we took that negative sign into account here already in this case. See, you cannot, meaning you already know the downward direction, right? That's why you already took this negative sign into account, meaning you are just getting the magnitude here. Okay, this gives you just the magnitude and the direction is already taken care of. Makes sense?